Hello, future engineers. Today's lecture video is about deflection methods, wherein I solve one problem in 8 different methods available in theory of structures. So these methods are by double integration, area moment method, conjugate B method, virtual work method, Castigliano's second theorem, 3 moment equations, slope deflection equations, and the matrix method. I already uploaded part 1 of this, but it was entitled 7 in 1 because I did not include matrix method for that case. But you might be interested in the matrix method, so that's why I incorporated the matrix method for this example. So if you're still new to my YouTube channel, don't forget to subscribe so that I will be inspired to do more lecture videos which will be beneficial to your studies. So here is the first problem. By 8 deflection methods, compute the slope and the deflection at points A and C. EI is constant. So first solution would be the double integration method. So let's solve for the reactions at B. Reaction at B times 10 minus 40 times 3 minus 20 times 8 times 9 equals 0. So reaction at B is equal to 156 kilonewtons. And summation moment at B equals 0, RD times 10, then minus 20 times 8 times 1 minus 40 times 7 equals 0. R sub D would be equal to 44 kilonewtons. So again, R sub D is equal to 156 kilonewtons, while RD is 44 kilonewtons. So let's consider a section in portion CDE beyond the 40 kilonewton to set up the moment equation. But before that, we have to extend the load to have only one moment equation and counter it with the same loading upwards, beginning with point C. So EI, so that's called X. So EI y double prime is equal to 156 times quantity x minus 3 plus 20 times x times 20 times x minus 8 times x minus 8 over 2. So 10 times quantity x minus 8 square. Again, 156 times quantity x minus 3. So this is x minus 3 plus this load here, 20 times quantity x minus 8 and moment arm x minus 8 over 2. So 10 x minus 8 square minus 20 times x over 2, or minus 10 x square, then minus 40 times quantity x minus 10, and that's the moment equation. So integrating EIY prime equals 78, call that equation A, 78 quantity x minus 3 square plus 10 thirds x minus 8 cube minus 10 thirds x cube minus 20 quantity x minus 10 square plus C sub 1. There is C sub 1, which is the slope divided by EI that represents the slope at A. Call that equation B. Then integrate again, EIY equals 26x minus 3 cubed plus 5 over 6x minus 8 to the fourth minus 5 over 6x to the fourth minus 20 over 3 quantity x minus 10 cubed plus C sub 1x plus C sub 2. Call that equation C. There is C sub 2 because A is not a support, so it will deflect. Then substitute the boundary conditions when x is 3 and x is 13, both yb and yd is 0. So x is 3, negative 5 over 6, 3 to the fourth. So this is 0. This is ignored because the quantity in parentheses is negative. Then ignored. Then plus C sub 1 times 3 plus C sub 2. Simplifying, 3 C sub 1 plus C sub 2 equals 67.5. Call that equation 1. And when x is 13, so 26 times 10 cubed plus 5 times 13 minus 8 is 5 to the fourth minus 5 over 6 times 13 to the fourth, then minus 20 over 3 times 3 cubed, plus c sub 1 times 13 plus c sub 2 equals 0. So simplifying, 13c sub 1 plus c sub 2 equals negative 2540, equation 2. So solving these two equations simultaneously by eliminating c sub 2 and then substitute the value of c sub 2 in equation 1, we get c sub 1 equals negative 260.75 and c sub 2 is 849.75. So as mentioned earlier, c sub 1 is theta A divided by EI, and c sub 2 is the deflection at A divided by EI. Therefore, theta A is negative 260.75 over EI, and delta A is 849.75 over EI. Then we substitute x is 8 to compute theta C and delta C. So for theta C in equation B, EI theta C equals 78 times 5 square, 0, minus 10 over 3, 8 cube, and ignore, then plus C sub 1, which is negative 260.75. So theta C is equal to negative 17.417 over EI, and in equation C, 26 times 5 cube, and this is 0, then minus 5 over 6 times 8 to the fourth, then ignore, then minus 260.75 times 8 plus c sub 2, which is plus 849.75. So solving for delta C is negative 3099.583 over EI. So this is the solution by double integration method. So we have solution by area moment method. So since we have already found RD 156 and RD 44 kilonewtons, so the best moment center here would be point B to get rid of spandrel that does not start with 0, so that the area would be simpler. So let's select B as the moment center. So we have moment of 44 times 10, 440 over EI. Then moment due to this 20 times 3 times 1.5. So, by the way, 44 times 5 is 220 over EI. So this is second degree, 20 times 3 times 1.5, 90 over EI, negative second degree. Then for this load here, 20 times 5 times 2.5 is 250 over EI, second degree also. Then moment of the 40 kilonewton load about B is 40 times 7, 280 kilonewton at 280 over EI. Then this is 40 times 2, so 80 over EI for deflection at C and theta C later. So first, let's compute deviation of point B relative to the tangent at B so that we can compute the theta at B, which is important in determining theta A and delta A. So EI division of D relative to B is 1/2 or 0.5 of 10 times 440 times 2/3 of 10, 20 over 3. So 0.5 of 10 times 440 times 20 over 3 minus the area of spandrel. Let's consider only area between B and D. Minus 1/3 of 5 times 250. This moment arm is 5 over 4, which is 1.25. So the distance of centroid from D is 8.75. So this is 1.25 or 5 over 4, 8.75 from the right. And for this triangle with base 7, 7 over 3 from B, and 10 minus 7 over 3 is 23 over 3 from the right meters. So minus 1/3 of 5 times 250 times 8.75 minus 1/2 or 0.5 of 7 times 280 times 23 over 3. So solving for division of D relative to B, it is equal to positive 3507.5 over EI So it means that that point D is above the reference tangent at B. So the reference tangent at B should be below, like that, so that D is above because the division of D relative to B is positive. And theta B, because it is sloping down to the right, it is negative. So what is the value? Negative division of D relative to B divided by 10. Because tangent of theta is just theta. So we will call this H division of D relative to B. This one is H sub C, and we have HA there. So by similar triangles, you can find HA and H sub C. This is theta B, which is expected negative. H sub C as to 5 equals H sub A as to 3 equals division of D relative to B 3507.5 as to 10. And because theta B is negative, remember that the ratio of opposite to adjacent is tangent of theta, and because theta is small, it is equal to theta itself, and because we anticipated that theta B is negative, we just put it negative theta B. So that HA is 1052.25, HC is 5 times 350.75, so that's 1753.75 over EI, and theta B is negative 350.75 over EI. Now let's consider portion AB. Take note that that's also theta B. So let's compute division of A relative to the tangent at B. And this is, because this is second degree, this is 3 over 4 or 0.75. And therefore this distance is 3 minus 0.75, 2.25. So division of A relative to the tangent at B is negative of 1/3, 3 times 90 times 2.25. So negative 1/3 of 3 times 90 times 2.25. Division of A relative to B is negative 202.5 over EI. So that means that point A is below the tangent at B. So and supposedly we have already found HA 1052.25. Division of A relative to B is only 202.5, and A should be below the reference tangent. Therefore, the deflection at A is positive. It is above the horizontal x-axis, because division of A relative to B is only 202.5 as compared to HA, or 3 times theta B, which is 1052.25. So if that is 3 meters, this is the horizontal line through B, and this is the tangent at B. This is division of A relative to B, which is negative. This should be the elastic curve, and A is above the horizontal x-axis. Therefore, deflection at A is positive of HA minus division, absolute value of division of A relative to B. So that's delta A, and that's the HA. So this is theta B, and the tangent at A is tangent line through A, and therefore this is theta from A to B, which is clockwise because the area is negative. So that's theta AB, and EI theta AB is the area, which is negative 1/3 of 3 times 90 over EI, so negative 90 over EI, and 90 over EI compared to theta B is, it is less considering absolute value. So theta B is the angle that the tangent at B makes with the horizontal, which is this entire angle here. That's theta B also, because this is the tangent at B. So this is theta B, and that is also theta B. So obviously this is theta A, which is negative again, because from the horizontal x-axis it rotates clockwise. Clockwise angle is negative. So theta A is negative of absolute value of theta B minus absolute value of theta AB. So theta A is negative absolute value of theta B, which is this, minus absolute value of theta AB, which is this one. So 350.75 minus 90 over EI, then make it negative. Theta A is negative 260.75 over EI, just like the answer in double integration. Then deviation delta A is positive. It is positive of absolute value of HA minus absolute value of deviation of A relative to B. So positive of absolute value of HA minus absolute value of deviation of A relative to B. So delta A is positive 849.75 over EI, just like in double integration. Then let's consider BC. So EI deviation of C relative to B. So let's compute the deviation of C relative to the tangent at B, and that is, we consider area between B and C. So let's divide the trapezoid into two triangles, and this trapezoid here into two triangles also. So we have quantity 1/2 or 0.5 of 5 times 440 over EI times 2/3 of 5. 2/3 of 5 is 10/3 plus 1/2 of 5 times 220 over EI times 5/3. Then minus quantity 1/3 of 5 times 250 over EI times 5 minus 1.25 is 3.75, because we sum up moment about C. So 5 minus 1.25 is 3.75. Minus the moment of this area of small triangle, quantity minus quantity 0.5 times 5 times 80 over EI times 5/3 minus 0.5 of 5 times 280 over EI times 10/3, because 2/3 of 5 is 10/3. So computing that, it is equal to positive 2,125 over 6 EI. So it means that the point C on the elastic curve is above the reference tangent at B. So if we draw the figure, this is the tangent at B. Point C should be above this reference tangent, and it should be somewhere here. Now, why do I know that it is only between the horizontal and this point? Because deviation of C relative to B is only 2,125 over 6, that's 100 plus only, whereas compared to 8 sub C, which is 1,000 plus. So the entire vertical distance here is 1,753.75, and this is only 2,125 over 6, which is roughly 300 something. So therefore, this is the deflection at C, which is below the original x-axis, so it is negative. So that's delta C, which is below the x-axis, so that's negative. The entire value of this is 8 sub C, which we already computed. So that's why EI theta BC, the area, is 1/2. Let's consider this as a trapezoid. So 0.5 of quantity 440 plus 220 times 5. Then minus spandrel, 1/3 of 5 times 250. Then minus trapezoid again, 0.5 of quantity 280 plus 80 times 5. So computing theta BC is 1000 over 3 EI, or 333.3. So because this is positive, the tangent at C, or from the tangent at B to the tangent at C, the rotation should be counterclockwise. But take note that theta BC is less than theta B in magnitude, because theta B is 350.75, whereas this is only 333.333. So this should be the tangent at C, and from the tangent at B to the tangent at C, the rotation is counterclockwise, because this is 333.3. So that's theta BC. Theta C, therefore, is the angle that tangent at C makes with the horizontal. So that's the horizontal. And this is theta C, which is negative because it rotates clockwise from the horizontal. Then the entire angle that the tangent at B makes with the horizontal is theta B. So theta C is expected negative, and it is negative of absolute value of theta B minus theta absolute value of theta BC. So EI theta C is absolute value of theta B, negative 350.75. It is negative anticipated. Then minus absolute value of theta BC, 100 over 3. So theta C is negative 17.417 over EI, just like in double integration method. And finally, delta C is negative, it is negative of absolute value of 8 sub C minus absolute value of deviation of C relative to B. So negative of absolute value of 8 sub C minus absolute value of deviation of C relative to B. So computing delta C is negative 3099.583 over EI, just like the third solution by conjugate beam method. So we copy the moment diagram by parts from area moment, then let's modify the supports. So A becomes fixed, B becomes interior pin or hinge, and D remains the same, a pin. So since BD is the simply supported portion of this beam, then let's consider BD, then we sum up moment about D first, then equals 0, so that we can solve theta B, and this is theta D. These are the directed thetas, positive direction thetas. So after we solve for theta B, we consider AB to solve for theta A and delta A. So first, 0.5 summation of moment about D equals 0. So we have 0.5 times 10 times 440 over EI. The moment arm is 20 over 3 minus theta. So we have theta B times 10 plus 0.5 times 10 times 440 over EI times 20 over 3. Then minus 1/3 of 5 times 250 over EI, then times 8.75, then minus 0.5 of 7 times 280 over EI times 23 over 3, then equals 0. Solving for theta B is negative 350.75 over EI, and next is we consider AB. So this is the positive theta A assumption and positive clockwise delta A. Summation forces y equals 0. So theta A, then minus theta B, which is going down, and theta B is negative 350.75, minus the area, which is minus 1/3 of 3 times 90 over EI, then equals 0. So solving for theta A is negative 260.75 over EI, just like in double integration method and in the other method. Then summation moment about A equals 0. So delta A plus negative 350.75 or theta B times 3 plus 1/3 of 3 times 90 over EI times 2.25, the moment arm about A, then equals 0. So delta A is equal to positive 849.75 over EI, just like the result in double integration and in area moment method. Next, we consider BC. So we have theta C, the positive rotation or shear, then counterclockwise positive delta C assumption. So let's divide this trapezoid into two triangles and this trapezoid two triangles. But before that, let's sum up forces vertical to solve for theta C. So we have theta B, which is negative 350.75 over EI, plus area of this trapezoid 0.5 of 440 plus 220 over EI times 5, then minus area of spandrel 1/3 of 3 times 5, 1/3 of 5 rather, times 250 over EI, then minus this trapezoid here 1/2 or 0.5 of 5 times quantity 280 over EI plus 80 over EI times 5, then equals 0. Minus theta C equals 0. We almost forgot theta C. Solving for theta C is negative 17.417 over EI, just like before. Then summation moment about C equals 0, so theta B times 5, so negative 350.75 over EI times 5, that's theta B. Then this triangle here, plus 0.5 of 5 times 440 over EI times 10/3, 2/3 of 5, 10/3, plus 0.5 of 5 times 220 over EI times 5/3, then minus 1/3 of 3 times of 5 times 250 over EI times 3.75, 5 minus 1.25, 3.75, minus the moment of this triangle, 0.5 of 5 times 80 over EI times 5/3. Then minus this big triangle here, 0.5 of 5 times 280 over EI times 10/3. Then minus delta C equals 0. So solving for delta C is negative 1399.58583 over EI, just like before. Solution 4 by virtual work method. So remember the reactions 1, 5, 6, and 44. Let's consider the following sections. So X for BC, that's X. Then C for this portion here, we have D2 for 3 meters, that one. Then we go the reverse to make it simpler. Then we apply counterclockwise unit couple at A. So the reaction at B should produce clockwise moment about D. So it should be upward. So reaction times 10 equals 1. So this reaction should be 0.1. The reaction at D should be also 0.1. Summation versus Y equals 0. So downward. So same sectioning, just like the original. So take note that 1 times theta is equal to summation of integral of moment at a section due to actual loads times moment at section due to virtual loads dx over EI. So let's make it EI because EI is constant. EI times 1 times theta A equals integral of, so since we consider positive moment, remember at the left is clockwise, at the right is counterclockwise. So this is counterclockwise, so it is negative 20 times x over 2, or negative 10x squared. Then for the couple, it's 1 only, counterclockwise, so it is 1, or negative 1 rather, moment at this section, because we consider positive moment at the left clockwise, at the right counterclockwise. So this is counterclockwise, so negative 1. Then for the next section, plus integral of 156x minus 20 times 3 plus x times 3 plus x over 2, or minus 10 times 3 plus x squared. Then for this section here, it is 0.1 times x minus 1. So the moment at this section, considering all forces to the left, is 0.1 times x, that's clockwise, yeah. Then minus counterclockwise, so minus 1. Then for the next section, this is counterclockwise, that's positive, remember. Integral of 44x, then times negative 0.1 times x, moment due to virtual load. Then plus integral of 44 times 3 plus x minus 40x, then times negative 0.1 times 3 plus x for the small moment. So evaluating the first integral, that's 90. The second integral is, you may evaluate that manually. Negative 2425 over 12. The third is negative 39.6, and the fourth is negative 1636 over 15. So combining, we can now compute theta A, which is equal to negative 260.75 over EI, just like before. Then for delta A, we apply an upward force at A. So the reaction at B should be downward. Reaction at B times 10 equals 1 times 13. So the reaction at B is downward 1.3. So that the reaction at B, summation versus Y, should be 0.3 upward. So same sectioning. Then we copy the moment due to actual loads, negative 10x squared. The new moment here is 1 times x. So integral 0 to 3 of negative 10x squared, then times 1 times x dx, plus integral of quantity 0 to 5, 156x minus 10 times 3 plus x squared. Then here we have 1 times 3 plus x minus 1.3x, moment due to virtual forces. Then third, plus integral of 44x, then times 0.3x. So 44x times 0.3x, both positive dx. And plus integral of 4 times quantity 3 plus x minus 40x, then times 0.3 times 3 plus x dx. So evaluating the first integral, negative 202.5. The second integral, 606.25. The third integral is positive 118.8. The fourth integral is positive 327.2. Then combining, delta A is equal to 849.75 over EI, just like before. Next, we apply counterclockwise unit couple at C. So the reaction at B should be clockwise about D. So reaction times 10 equals 1. So again, this is 0.1 upward. And the reaction at D should be 0.1 downward by sum up forces vertical. So same sectioning. And take note that due to virtual forces, the moment in this section is 0. So the first term is 0. So EI 1 times theta C equals integral 0 to 3 of negative 10x squared times 0. So this is 0. Then for the second section, plus integral 0 to 5 of 156 minus 10 times 3 plus x squared times 0.1x only dx. Then plus for the third section, integral of 44x times negative 0.1x dx. And for the last section, integral of 44 times 3 plus x minus 40x times negative 0.1 times 3 plus x dx. So evaluating the first integral, it is equal to 0. The second integral is 131.25. The third is negative 39.6. The fourth is negative 1636 over 15, just like the answer above. So theta C is equal to negative 17.417 over EI, just like before. And finally, we apply a unit upward load at C. Then the reaction at B should be downward as well as at C. Since C is midway between B and D, so 0.5 downward at B, 0.5 downward at D also. So same sectioning. Again, the moment here due to virtual force is 0. So the first term again for EI delta C is 0. Negative 10x squared times 0 dx. Second term plus integral 0 to 5, 156x minus 10 times 3 plus x squared times negative 0.5x, only the moment here. Third integral is integral from 0 to 3 of 44x times negative 0.5x dx. And last, integral of quantity 44 times 3 plus x minus 40x times negative 0.5 times 3 plus x. That's the moment. The first integral is 0. The second is negative 656.25. The third is negative 198. The fourth is negative 1636 over 3. Combining, so delta C is equal to negative 3099.583 over EI, just like in the other methods. So next, let's have solution 5 by Castigliano's second theorem. So this time we apply a unit couple C at A counterclockwise. Then due to the reactions, it was 156. But due to the couple here, we have reaction times 10 equals couple. So this reaction at B would become 156 plus 0.1 of C. So the reaction at D would be 44 minus 0.1 of C. So sectioning the same. So first moment at this section, so EI times theta A equals integral of negative 10x squared negative C. Then derivative is negative 1. The derivative of this moment equation is derivative with respect to C is negative 1 dx. Then for the second section, quantity integral of quantity from 0 to 5 of 156 plus 0.1 C times x minus 20 times 3 times quantity 3 plus x, 3 plus x over 2, or 10 times 3 plus x squared, then minus c, then the derivative of this moment equation is 0.1x with respect to c, so 0.1x, then minus 1. So that's why we have 0.1x minus 1 here. For the third section, it is integral of quantity 44 minus 0.1c times x. The differential is negative, partial derivative is negative 0.1 of x dx. So 44x, or 44 minus 0.1 of c times x. So the derivative is negative 0.1 of x dx, 0 to 3. Then plus integral of quantity 44 minus 0.1 of c, quantity 3 plus x minus 40x. Then the derivative is negative 0.1 of 3 plus x dx. See it? So before integration, prior to integration, since c is 0, we only apply that. So set c to 0, 0, 0, 0, and take note that the remaining term, integral of negative 10x squared times negative 1 dx, is the same as that of virtual work method. So that's why this is positive 90. Second is negative 2425 over 12. Third is integral of 44x times negative 0.1x is negative 39.6. Fourth is integral of 44 times 3 plus x minus 40x times quantity negative 0.1 of 3 plus x. So that would be negative 1636 over 15. So that's why theta A is negative 260.75 over EI, just like in virtual work method. Then next, we apply unit upward force P at A. So the reaction here would become, that's upward. So the due to P, this should be downward. So 156, because P times 13 divided by 10 is 1.3. So the reaction at B would be 156 minus 1.3 of P, while at D is 44 plus 0.3 P. So same sectioning. We have EI delta A is equal to integral from 0 to 3 of P times x minus 10 times x squared. Then the derivative is x dx, derivative of px with respect to P is x. Then plus integral of quantity 156 minus 1.3 P times x. Then minus 10 times 3 plus x squared plus P times 3 plus x. Derivative is negative 1.3x, then 3 plus x. So 3 plus x, negative 1.3x dx. So third is integral of quantity 44 plus 0.3 P times x. The derivative is 0.3x dx. Then the fourth integral is integral of quantity 44 plus 0.3 P times 3 plus x minus 40x. The derivative is 0.3 of 3 plus x. So setting the value of P to 0 before integrating. So the first integral would be same as that of virtual work method, so negative 202.5. The second integral is 606.25. The third integral is 118.8. The fourth integral is 327.2. So combining, delta A is equal to 849.75 over EI. Then we remove P, we apply counterclockwise couple at C. Same sectioning. Then the reaction here would be due to C alone, because due to the actual loads, it's 156 upward. So reaction times 10 equals C. So therefore the reaction at B is 156 plus 0.1 of C. And here it's 44 minus 0.1 of C. So first integral is negative is 0 because it is negative 10x squared. Then the derivative, there's no C there, so 0. So EI theta C is integral of negative 10x squared times 0. The derivative of negative 10x squared is 0 because the variable is P. Then plus integral of quantity 156 plus 0.1 of c times x minus 10 times 3 plus x squared. Then the derivative is 0.1 of x dx. Then plus integral of quantity 44 minus 0.1 c of x. Then derivative is negative 0.1 of x dx. Then lastly, we have integral 0 to 2 of quantity 44 minus 0.1 of c times 3 plus x minus 40x. The derivative is negative 0.1 of 3 plus x dx. So prior to integration, set the value of c to 0. Then the first integral is 0. The second is 131.25. The third is negative 39.6. The fourth is negative 1636 over 15. Then combining, theta c is equal to negative 17.417 over ei, just like before. Then we apply unit upward load. We apply upward load of P at C. So the reaction here would become 156 minus 0.5 P, because P is at the center. So upward, then this should be downward. So 156 minus 0.5 P on the right side at the 44 minus 0.5 of P. So the first integral here is again 0 because it does not involve P. So integral of negative 10x squared times 0 dx. Then in the next section, it is integral of quantity 156 minus 0.5 P of x minus 10 times 3 plus x squared. Then derivative is negative 0.5 of x dx. Then plus integral of quantity 44 minus 0.5 of p times x. Then derivative negative 0.5 x dx with respect to p. Then lastly, integral 0 to 2 of quantity 44 minus 0.5 p times 3 plus x minus 40 times x. The derivative is negative 0.5 of 3 plus x dx. So set value of p is 0. And the first integral is 0. The second integral is negative 656.25. The third is negative 198. The fourth is negative 1636 over 3. So combining, delta C would be negative 1399.583 over EI, just like before. So solution number 6 by three-moment equations. So to solve for deflection at A, we consider A, B, D. Span AB and span BD. So remember the reactions. And moment B is negative 20 times 3 times 1.5 or negative 90. But moment BA, that is moment BC or moment BD, negative 90. But okay, moment B is negative 90. Moment at C is 44 times 5 minus 20 minus 40 times 2. And that would be 140 kilonewton meter positive. So in span ABD, moment at A is 0, plus 2 times moment at B is negative 90, times span AB, which is 3 plus 10. So 2 times negative 90 times quantity 3 plus 10, plus moment at D is 0. So MD is 0. This is the three-moment equation. I hope that you're familiar with that, or you already know the three-moment equations. Then plus 6A1A over L1. 6A1A over L1 for this span AB, which is in three-moment equation, we consider this as simply supported, although this is an overhang, simply supported, and there's a formula for 6A1A over L1, which is WL1 cube over 4. So in this case, double 20 times 3 cube over 4. For the second span, this is the moment due to the load. 20 times 5 times 2.5 is 250. Moment due to the 40 kilonewton load at B, because BD is treated as simply supported or separate simply supported beam. 40 times 7 is 280. And second degree, this is 280. 250 plus 280 is 530. Therefore, the moment of the reaction here, if this member BD is simply supported, is also 530, the sum of 250 and 280. So that should be 530. Remember that this is three-moment equation. And in three-moment equation, the span is considered simply supported, and therefore the moment of the loads should also be the moment of the reaction at same support, because the end simply supported beam has zero moment. So that 6 for span BD, the value of 6A2B over L2 is 6 over 10. 6 over 10 times quantity area of this triangle, 0.5 times 10 times 530 times 20 over 3, minus 1/3 of 5 times 250 times 8.75, minus 1/2 or 0.5 of 7 times 280 times 23 over 3, just like before. So 6A2B over L2 for span BD is equal to 3,904.5 kilonewton meter square. So plus 6A1A over L1, or 6A1A over L1 for span AB is 23 cube over 4. That's the formula. For 6A2B over L2, so this is the value, plus 3,904.5, then equals 6EI times quantity HA over 3. Then remember that we have to draw horizontal line through B. So definitely A will be displaced either up or down. Then let's assume that it is above. So A is above the horizontal line through B. So it is HA over 3. While HD over L is HD over 10 is 0, because the horizontal line through B passes through the support B. So 6EI times HA over 3 plus 0 over 10. So we can solve HA here. So HA is positive 849.75 over EI. That means that point A, after it is displaced, is above the horizontal line through B, which is the x-axis. So therefore, the deflection at A is positive because it is above the horizontal line. So it is delta A 849.75 over EI. Now how about theta A? So we draw the elastic curve. So this is the elastic curve. The tangent at A is down to the right. And let's compute EI division of B relative to A. But before that, we draw the moment diagram by parts of the portion AB. This is delta A or HA, which is equal to 849.75. Then the angle that the tangent at A makes with the horizontal is theta A. And if this is correct, then theta is negative. And this is 20 times 3 times 1.5 is 90 over EI. So this is a negative area. So second degree, EI division of B relative to A is negative 1/3 of 3 times 90 over EI times moment arm is 3/4. So 3 divided by 4. This distance is 3/4 because we sum up moment about B. So division of B relative to A is negative 67.5 over EI. So it means that point B is below the reference tangent at A. So this is correct figure. This is division of B relative to A. And this is the deflection at, this is HA minus division of A relative to B, division of B relative to A. And this is supposedly 3 times theta A, because this is a right triangle. The opposite is distance times theta A. So because theta A is negative, so we equate 3 theta A to absolute value of HA, or 3 theta A as negative of quantity absolute value of HA minus absolute value of division of B relative to A, because theta A is negative. So theta A is negative 1/3 of absolute value of HA minus absolute value of division of B relative to A. So, or in other words, 3 theta A, 3 times theta A is negative of quantity absolute value of HA minus absolute value of deviation of B relative to A, because theta A is expected negative. So theta A is negative 260.75 over AI, just like before. So next, we consider the beam BCD, or the spans BCD. So moment at B is negative 90, then span BC is 5, plus 2 times moment at C, which is 2 times 140 times 5 plus 5. So this is the horizontal line through C. This is HB, this is HD, and this is delta C. So horizontal line through C to original x-axis delta C. So take note that HB equals HD equals delta C. So if this is correct, then delta C is negative. So plus 2 times moment at C, which is 140, times quantity 5 plus 5, plus moment at D, because we consider BCD, moment at D is 0, times 5, then plus 6A1A over L1. Again, we have this uniform load. BC is a simply supported beam in our thinking or imagination. So the value of 6A1A over L1 is 6A1A over L1 is 25 cube over 4. Then 6A2B over L2, because that's a concentrated load only. So we use the formula PB over L, quantity L square minus B square, or 40 times 3 divided by 5 times quantity 5 square minus 3 square. Then equals 6EI times HB over 5 plus HD, which is equal to HB over 5 also, because span CD is 5. So solving for HB is positive 1399.583 over EI. It means that both B and D are above the horizontal line through C. They are above the horizontal line through C, but we are computing delta C, which is referred from the horizontal x-axis. So therefore, delta C is negative, and it is the negative of this value. So delta C is negative 1399.583 over EI, and that's the same as before. Finally, the better deviation to compute is deviation of D relative to C, because we only have smaller area here. So remember, that's 40, and the moment due to 44 about this end is from area moment theorems is 220, or 44 times 5 to 20 over EI, and 40 times 2 is 80 over EI. So let's consider this area for segment CD, and let's evaluate 6A2B over L2. So EI, deviation of D relative to C, equals 0.5 of 5 times 220 over EI times 2/3 of 5, 10/3, minus 1/2 or 0.5 of 2 times 80. The moment arm is 5 minus 2/3. 5 minus 2/3 is 13 over 3. So minus 0.5 of 2 times 80 over EI times 13 over 3. So division of D relative to C is equal to 4460 over 3. Expressed in decimal, that's greater than HB or HD. So the division of D relative to the tangent at C is greater than HD. So that means the tangent at C should be depressed downward, going down, so that this vertical distance is greater than HD. And that's positive. So meaning D is above the reference tangent. So this is, if this is theta C here, and the distance is 5, then this is 5 times theta C, and the whole distance, vertical deviation, is deviation of D relative to C. So since theta C again is expected negative because it is inclined down to the right, so 5 theta C is equal to negative of absolute value of deviation of D relative to C minus HD. So in other words, division of D relative to C minus HD is 5 times theta C, but because theta C is negative, we set the difference negative. So 5 theta c is negative absolute value of deviation of d relative to c minus absolute value of hd, which is equal to hb. Then we can solve theta c equals negative 17.417 over ei. So that's it for solution by three-moment equation. Solution 7 by slope deflection equations. So look at the figure. So let's compute. Remember that moment BD is negative 90, but moment BA is positive 90. Moment BD or BCD is negative 90, while moment BA is positive 90. Moment CD is, remember that 140 kilonewton meter, that's moment CD, but moment CB or moment C to A is negative of 140. So moment BA is positive 90 kilonewton meter, and moment CB is negative 140 kilonewton meter. So there are two equations, slope deflection equation. If the far end is free, then it is moment near to far 3ei over L times quantity theta near minus P, or slope of the chord, then minus fixed moment sa left, which is negative, minus 1/2 fixed moment far. Then if the far end has also moment, then use moment near to far is 2ei over L, quantity 2 theta near plus theta far minus 3 times P, or delta over L, then minus for the left end minus fixed moment near. So left minus right plus, if the position of the point is at the right. So for fixed moment, for portion BCD, for example, let's consider this strip, and that is 20 dx, and our x is from C to that strip. So moment BD is negative 90, and because the moment at D is 0, so we use 3ei over L, so 3ei over 10. Theta near is theta B minus P. There is no rotation of the chord BD because B and D are supports, so it is just 0. Delta is 0 divided by 10, so that is still 0. Then minus fixed moment at the left. Fixed moment at the left consists of fixed moment due to this load and this load here, concentrated load here. For the uniform load, we have integral of negative integral of 20 times, this is 5 minus x, so its distance from the right is x plus 5 quantity square divided by 10 square. So 20 dx, 5 minus x, x plus 5 square over 10 square. Then plus 40 times 40 times 7 times 3 square over 10 square. So that is also negative. So this is quantity, right? This is negative of this and negative of 40 times 7 3 square over 10 square. Minus 1/2 fixed moment far. So the moment here is positive. So minus 1/2 of, we use the same integral, interchange 5 minus x and x plus 5. So 5 minus x is square, x plus 5 is no more. 7 is squared, 3 is no more. So minus 1/2 of positive 20 dx, 5 minus x square, x plus 5 over 10 square, then plus 40 times 7 square times 3 over 10 square. Close. So simplify, negative 90 equals 0.3 ei theta b. Then the value of this integral and this value is negative 8387 over 60, while minus 1/2 of this quantity here is minus 6653 over 120. So from there we can solve theta b, which is equal to 350.75 over ei, and because this is positive, it is clockwise, because in slope deflection equation, clockwise is positive. Clockwise rotation, clockwise rotation of the chord, that's positive. But clockwise slope or clockwise rotation with respect to the global orientation is negative, because counterclockwise is positive, just like in double integration method. So theta b is 370.75 over ei clockwise, and we use this because we are using slope deflection equation. Next, we compute MBA. So let's consider BA. This is the diagram. The rotation, let's assume that the rotation of the chord is clockwise again. So this is PAB, which is treated positive. Delta A is also treated positive because the chord is rotating clockwise. So MAB, moment at A is 0, and because there is moment at B, so we use 2EI over T instead of 3EI over L. So 2EI over L, L is 3 between A and B. So 2 theta near, 2 theta A plus theta B, this is theta B, minus 3 times P. And P is delta A divided by 3, and that delta A over 3 is positive because it is clockwise rotation PAB. Then my near end is A, so negative 23 square over 12. That's the fixed end moment formula for uniformly distributed load. Then at the right side, no more, because this is 2EI over L, so fixed end moment near only. So simplifying, we have 2/3 times 2 is 4/3 theta A. Then 2/3 times negative delta A, because this 3 over 3 is negative 1, is 2/3 delta A. Then 20 times 3 square over 12 to the left is positive, times 3 times minus 2/3 of 350.75. So minus 2/3 of 350.75 is negative 1313 over 6 EI. Call that equation 1. Then next is moment BA. Moment BA is positive 90, and this is 3EI over L. 3EI because moment at the far end, which is A this time, near end is B, far end is A, is 0. So that's why we use 3EI over L. Quantity theta near, theta B, then minus P. P is delta A over 3, which is positive because clockwise rotation. Then the fixed end moment at B is positive, so 20 times 3 square over 12, then minus 1/2 fixed end moment at A is the same, minus 1/2 of negative 20 times 3 square over 12. So simplifying, actually we can solve delta A this time because this is the only unknown. So delta A is 849.75 over EI to solve this equation. So that's it. 90 minus 20 times t squared over 12 minus 1/2 of 20 times t squared over 12. And after that, minus 350.75 times negative 3, that's delta A. So it is positive 849.75 over EI. Since it is positive, it means that it is upward, or this rotation is correct. So delta A is positive 849.75. Substitute into equation 1, 4/3 theta A minus 2/3 of 849.75 over EI equals negative 1313 over 6 EI. So we can solve theta A. If theta A is positive, it means clockwise, but clockwise rotation is actually negative. So clockwise is negative because the positive slope or positive rotation is counterclockwise. So theta A is negative 260.75 over EI. Next, let's consider MBC. MBC is negative 90, and it is 2 EI over L, 5L, times 2 times theta B plus theta C minus 3 times delta C over 5. So again, we expect that delta C is going down, so that the chord joining B and C is again rotating clockwise. So this is the elastic curve. So that's why we have minus 3 times delta C over 5. This is treated positive because the rotation of the chord from B to C is clockwise. Then, because we use 2EI over L because there is moment at C, and so the moment at B, fixed end moment at B, is due to this uniformly distributed load, which is negative 25 square over 12. So minus 20 times 5 square over 12. Then that's it. So simplifying, we have theta C minus 3/5 of delta C equals negative 2467 over 3 EI. So theta c minus 3 delta c over 5 equals negative 90 plus 20 times 5 square over 12. Then after that, times 5 over 2. Then minus 2 times 350.75. That's the result. Then MCB, C to B, we use the same formula, 2EI, but MCB is negative 140. So negative 140 is 2EI over 5 times quantity theta B plus 2 times theta C minus 3 times delta C over 5. Then because the near end is C, so this is right of B. The fixed moment here is positive 20 times 5 square over 12. That's the only thing. Then the second equation, the third equation rather, is 2 theta c minus 3 delta c over 5 is equal to negative 140 minus 20 times 5 square over 12 times 5 over 2, then minus 350.75, and you will get negative 9659 over 12 EI. So solving equations 2 and equation 3 by elimination of delta c, then substitute in one of these equations to solve for theta c, you will get theta c equals 17.417 over EI, since that is positive and this is slope deflection equation, so clockwise. And delta c is positive also because our assumption is it's going down, so that the chord rotation is clockwise, 1399.583 over EI, but it is downward, so that our assumption is correct. So to finalize the answer, theta c is 17.417. It is clockwise, so it is negative, and delta c is negative 1399.583 over EI, just like before. Finally, we have the last solution by matrix method. So this is the beam. So let's consider BD as a beam, so that we only have two unknowns and we can solve the slopes at B and D. So we consider AB as cantilever with moment, which is clockwise, 20 times 3 times 1.5. So this is 90. 20 times 3 times 1.5 is 90. Then for BD, let's compute fixed moments. No? So that would be integral of, again, fixed moment formula, 20 dx. So it is counterclockwise. 20 dx times, if we set this as our x, so this is 5 minus x, and the other distance is x plus 5, quantity square. So this is also the direction of moment, fixed moment for D. Remember that in matrix method, we consider BD as fixed-ended. So fixed moment BD is equal to integral 0 to 5 of 20 dx times 5 minus x, x plus 5 square over 10 square plus 40 times 7 times 3 square over 10 square. So it is represented by this moment direction. So it is equal to 8387 over 60 kilonewton meter. While fixed moment B is equal to same integral, except that 5 minus x is now square, x plus 5 raised to 1 over 10 square, then plus 40 times 7 square times 3 over 10 square. And the direction is already indicated in the figure. So fixed moment dB is 6653 over 60 kilonewton meter. So remember that the nodal loads are opposite to the moments here. So the technique is, this is clockwise, so 90 minus this moment here, which is 8387 over 60. If the result is positive, it means counterclockwise. If the result, the nodal load is counterclockwise. If the result is negative, it means that the nodal force is clockwise. So 90 clockwise minus counterclockwise, the result is, if it is positive, so it means counterclockwise. 90 clockwise minus this counterclockwise moment. So if 90 is greater than a counterclockwise moment, the result will be clockwise. But the load is opposite to the clockwise, so it's counterclockwise. So that's why the shortcut is you treat 90 clockwise as positive minus counterclockwise negative. Whatever is the result, that's the final nodal load. So 90 minus 8387 over 60, because it is negative, so you have here a negative result or clockwise, and you make it positive, 2987 over 60. Since at the other end D, there's no other load, this is clockwise, so the nodal load should be opposite, counterclockwise. So 6653 over 60 counterclockwise at D. So we have only one member. The stiffness matrix or the stiffness of this element will be 12 EI. We consider EI as 1 because EI is constant, divided by 10 cube. So consider BD, force F3, then negative 2987 over 60, F7, not important because there's no displacement, then 6653 over 60 counterclockwise positive. So 0.012 is 12 times 1 divided by 10 cube, that's 0.012. 0.06 is 6 times EI1 over 10 square, so 0.06. Then the negative of the first entry here, then you copy the second entry. Then this is 6 EI over L square, so 0.06. 4 EI, 4 times 1 over L, 10. So 4 over 10 is 0.4. Then the negative of this first entry. Then this is 1/2 of 0.4. 2 EI over L. 2 times 1 over 10, so 0.2. The third row elements are the negatives of the first row elements. The fourth row elements are, you copy the second row elements but interchange the second and the fourth column position. So 0.4, you have 0.2 here, then 0.4 should be here, and the rest is the same. Then we have delta B, which is 0, theta B, which is to be determined, delta D, which is 0, and theta D, which is to be determined. So we only expand this second and fourth row. Then we have negative 2987 over 60, 6653 over 60 equals EI of 0.4, 0.2, second, fourth, 0.2, 0.4, then 0.06 first and third, plus, but because these are 0, theta B 0 and delta D 0, first and third rows rather, so that would be the result, because anyway 0.06 times 0 and 0.2 times 0 is 0. So therefore theta B and theta D can now be solved. It is the inverse of this 2 by 2 matrix times this matrix here. So theta B, theta D is equal to the inverse of 0.4, 0.2, 0.2, 0.4 times this second or row matrix. So divided by EI. So finally, theta B and theta D can now be solved. It is equal to negative 350.75 over EI and theta D 452.583 over EI. Remember theta B from area moment method and from conjugate beam method, it was negative 350.75 over EI. So our solution is correct. Next, we consider just AB as fixed. So if A and B are fixed, then we have the same moment, which is 20 times 3 squared over 12. 20 times 3 squared over 12 is 15. And that's counterclockwise here, clockwise. It's also 15 by symmetry. And therefore, the nodal load at A would be the opposite to these moments here. So we have 30 downward at A, or 1, 2, 30. And this is counterclockwise, so clockwise, negative 15. And we find theta A, delta A, and theta A. So B, we already know theta B, which is negative 350.75 over EI. So considering AB, the stiffness would be, or the stiffness elements would be 12 EI1 over 3 square. So we have negative 30, negative 15, then F3, then F4 equals EI. So 12 times 1 over 3 cube is 4 over 9. 6 times 1 divided by 3 square is 2/3. Then the negative of the first, then copy the second, then 6 times 1 over 3 square is 2/3. This is 4 times 1 over L. 4 times 1 over 3 is 4/3. Then the negative of this value, then 1/2 of this value is here. The negative of the first row, then copy the second row except that we interchange the second and the fourth values. So 2/3, 4/3. Yeah, same first and third column elements. Then we have delta A, theta A, then delta B, which is 0, and theta B, which is negative 350.75. But we want to expand only the first two rows. So 4 over 9, 2/3, 2/3, 4 over 9 times delta A, theta A, then plus this 2 by 2 matrix, negative 4 over 9, 2/3, negative 2/3, 2/3 of 0 times negative 350.75. So negative 30, negative 15 equals EI, this 2 by 2 matrix times delta A, theta A, then plus this 2 by 2 matrix, negative 4 over 9, 2/3, negative 2/3, 2/3 times 0 and negative 350.75 over EI. So negative 4 over 9 times 0 is 0, then 2/3 of negative 350.75 is negative, then transpose to the left, add to negative 30, it becomes 1,223 over 6. Then for the second value here, negative 15, negative 2/3 times 0 is 0, 2/3 of negative 350.75 is negative, so negative to the left, so positive times negative 15 is positive 1313 over 6. Then we have EI, this 2 by 2 matrix times delta A, theta A. So solving for delta A, theta A, this is the inverse of this matrix times this matrix here divided by EI. So the inverse of 4 over 9, 2/3, 2/3, 4 over 9 times this matrix here. So the result, delta A is equal to 849.75 over EI, just like before, and theta is negative 260.75 over EI, just like before. Then for portion BCD, let's consider BCD because we want to know the delta C and theta C. So remember that we consider BC as fixed, CD as fixed, and we have two members here. So consider BCD, each member has a length of 5, so they have the same member stiffness. So this part is treated cantilever. Remember that the moment here is negative 90 or 90 clockwise because we have 20 times 3 times 1.5, 90. So the fixed end moment here is 25 square over 12 is 125 over 3. Remember that B is imagined fixed, C is also imagined fixed. So the moment, fixed moment here is clockwise 125 over 3. Then since same moments at the left and the right, the cancel effect, then summation forces Y equals 0. Reaction times 2 because the reaction at B is also the same at C by symmetry equals 20 times 5. 20 times 5 is 100 divided by 2, so each reaction is 50. So that's why that's 50. The moment is clockwise 125 over 3. For the other side, fixed end moment is 40 times 2 times 3 square over 5 square. That's so here it's 19.2. 40 times 3 times 2 square over 5 square is 19.2 clockwise. Here it's counterclockwise. 40 times 2 times 3 square over 5 square, it's 120. It's 28.8 here. So at B, the nodal load would be 90 minus 125 over 3. The result is positive. So that's why we have 145 over 3. 90 minus 125 over 3 is positive 145 over 3. So it should be counterclockwise. Then at C, so we have 50. The 25.2 reaction is you sum up moment about D, so reaction times 5 minus 40 times 3 minus 28.8. We have a couple here of 28.8 counterclockwise. So again, summation moment at D is right reaction at C right times 5 plus 19.2 equals 40 times 3 minus 28.8. Or, sorry, reaction times 5 plus 19.2 minus 40 times 3 minus 28.8 equals 0. Or the reaction here is 40 times 3 plus 28.8 minus 19.2 divided by 5. So you get 25.92. So 25.92 plus 50 is 75.92 upward, but the nodal force is opposite to that. So that's why you have 75.92 kilonewtons downward. For the moment, 120 over 3 minus 28.8, that would be positive. 125 over 3 minus 28.8 is positive. 193 over 15, that's why we have counterclockwise moment here. Then of course, at the right end, it's 19.2 clockwise, so the nodal force is counterclockwise 19.2. And the reaction is not important because the displacement at D is 0. Just like at B, the displacement is 0, so we don't mind the vertical force. So KBC is equal to EI 12 EI over 5 cube, because BC is equal to CD. They have the same length, same EI. So 12 times 1 over 5 cube is 12 over 125. 6 times EI 1 over 5 square is 6 over 25. Then copy the first element, then make it negative. Copy the second element. This is 6 EI. 6 times 1 over 5 square is 6 over 25. 4 times EI 1 over L 5. So 4 over 5 is 0.8. Then copy this, then make it negative. Then half of 0.8 is 0.4. Then the third row elements, the negative of the first row elements. The fourth row elements, you copy the second row elements, except that we interchange the second and the fourth elements. So 0.8 is now here and 0.4 is here. So that's it. That's all. The numbering important is if this is 1, 2, 3, 4. So 4, 5, 6, 8. Rotation is 8. So 4, 3, it is 4, 5, 6, 8. 4, 5, 6, 8. But member BC is 3, 4, 5, 6. Member CD is 5, 6, 7, 8. So member CD is EI, factor out EI, then we have same, because they have the same length and EI. And the numbering is 5, 6, 7, 8. So that's it. So the numbering is 5, 6, 7, 8 for member CD. 5, 6, 7, 8. But the common is, this is theta, so this is 4. Then displacement and rotation 5, 6. Then rotation 8. So 4, 5, 6, 8. So nodal forces, we have 4, 145 over 3. 5, negative 75.92. 6, positive 193 over 15. Then 8, positive 19.2. EI, so this is 4, 4, 4. So let's put the number first. 4, 5, 6, 8. Then vertical 4, 5, 6, 8. So this is 4, 4. So 4, 4 is 0.8. And there's no other 4, 4 here. So 0.8. 5, column 5, row 4. 5, row 4 is negative 6 over 25. So negative 6 over 25. Then 5, 4. And there's no other. Then we have 6, 4. 6, 4 is 0.4 here. So we have 0.4. Then 8, 4. There's no 8, 4. So 0. Then copy this row into this column here. Then this is 5, 5. So 5, 5 is 12 over 125 plus 5, 5 here is 12 over 125. So 24 over 125. 6, 5, negative 6 over 25. And we have positive 6 over 25. So the result is 0. 6, 5. Then 8, 5. 8, 5 is 6 over 25. So that's why we have 6 over 25. Then copy this 0 and 6 over 25 here. Then this is 6, 6. 6, 6 is 0.8 plus 0.8. So 1.6. Then 8, 6. There's only 186.4, so 0.4. This is, then copy 0.4 here because the matrix is symmetrical. Then lastly, we have 8, 8. 8, 8 is only 0.8, so 0.8 here. So we multiply by the known displacement at 4. Theta B is negative 370.75 over EI. And theta 8 or theta D is 452.583 over EI. These are the unknowns. So let's expand rows 5 and 6. So negatives, we have 24 over 125, 0, 0, 1.6 times delta C, theta C, plus EI of negative 6 over 25, 6 over 25, then 0.8 times this displacement, negative 350.75 over EI, and 452.583 over EI. So negative 75.92, 193 over 15 equals EI of 24 over 125, 0, 0, 1.6 of delta C, theta C, then plus EI times negative 6 over 25, 6 over 25, 0, 0.4, sorry, 0.4 and 0.4 of displacement, negative 350.75 over EI, 452.583 over EI. Since the other partner of the matrix is 0, then we can now solve delta C and theta C by just one equation. So negative 75 point, let's expand this first. Negative 6 over 25 times negative 350.75 is equal to, then plus 6 over 25 times 452.583. The result transposed to the left, then add to negative 75.92, then it will be equal to negative 75.92 equals 24 over 125, this one, theta delta C, then negative 6 over 25 times negative 350.75 plus 6 over 25 times 452.583 is 192.8. So the only unknown here is delta C, so we can solve delta C equal to negative 1399.583 over EI, just like before. Then 193 over 15 equals, there is EI here, so EI times 1.6 theta C, then 0.4 times negative 350.75 plus 0.4 times 452.583 over EI is 40.7332 over EI. Then combined in the left side, then you will have theta C equal to negative 17.417 over EI, just like before. So that's it. And I will no longer talk because the solution is very, very long. So thank you for watching.